Oh, hi there. I didn't see you come in. I was just playing with the forks here. You see, I'm actually a member of a forkestra. Now, these forks, though, aren't just for musical delight. They're actually for a lesson. Today's lesson is about Chapter 10 in math. It's all about patterns and expressions. So there are four components to this particular unit. You can skip ahead if you need to see this in multiple viewings. Our first one is going to be looking at identifying patterns. Our second topic in the chapter is looking at writing patterns, writing specifically expressions. Our third one will be looking at solving the values of expressions. And our fourth and final topic will be about graphing linear relations or graphing these patterns that we see. Now, some of these words may not be familiar to you, but stay tuned to the corresponding chapters and hopefully they'll be very familiar to you, like an old friend or a favorite blanket from your childhood. So you may have heard the term patterns before. Now, a pattern, I remember learning about this in kindergarten. It was really fantastic. I know both of the years that I attended kindergarten, we talked a lot about patterns. So there are all kinds of patterns. There are patterns on your clothes. Take a look at this lovely stripe here. We predict that this stripe will go all the way around to the back, right? Does it? Let's check. Yeah, oh my goodness, it did. I didn't actually know. A pattern is something we can predict will repeat, or that we know that based on perhaps if it's increasing, like let's say every year that you live, an extra 12 months is added to your age. So we can predict if you live 3 years that you'll be 36 months old. Now, hopefully you live to be older than that, but hey, it's about the quality of life, right? Not how long it is. Let's take a look at another pattern. This is a Christmas bag. I like to keep my Christmas bags up here. That way Christmas is all the way around. So take a look. Let's start looking at this little red stripe right here. Here we go. The red stripe right here. So it goes red, light green, darker green. That's emerald green. Yeah, lovely crimson hue right here. This is what my face looked like when I couldn't get patterns right. And then white right here with the black stripe. And then some green again, nice lovely puke green that's called, or chartreuse. Goes on, white stripes. All of a sudden though, take a look. We're back to our original red stripe. And what follows it, once again, is our lime, or yeah, this is the puke green. This is lime green. This is my grandpa's favorite color. Emerald. And it continues on, right? So you see the same pattern continues. And something we can establish. And we would know what to expect later on in the sequence of that bag. So we'll be looking at the patterns. So let's take a look though at patterns of numbers. And let's take our old friends, the forks, back. So let's say we're counting the number of tines or the prongs that are on the fork. So if we have one fork, we would have 4 prongs, right? How many prongs would we have though if we have 2 forks? For all you folks at home, put in your guesses. Let's see. We have 1, 2, 3, 4, 5, 6, 7, 8. Oh, cut myself on that one. Oh, see, math is dangerous. Got to be a professional to do this. Okay. Okay, so that was 2 forks. What if we had 5 forks? How many prongs would we have? I bet you can't get this. Now, all the forks are the same. I'm not tricking you here. I'm not some kind of witch. Take a look here. 5 forks, and one of them is being held to the side. Okay. Aha. And let's count them together, shall we? It's like Dora the Explorer, but less violent. Okay. So we got 4. I'll put them down. So this is difficult holding 5 forks. 4, 8, 12, 16, and 20. If you knew that there were 20 prongs to 5 forks, then congratulations. That means you must have passed the 2nd grade. Now I'm going to throw a little bit of a tricky thing at you. We're going to modify one of these forks. We're going to customize it, kind of like a biker gang will, put little decals on their bikes. Okay, so I'm going to snap these forks off, or these prongs off. Or you know what? Because this plastic is proving to be resilient, let's just pretend that it's not there, okay? It's like a dark family secret. Okay, so we're going to still count the number of prongs. That's still what we're looking for because it's this bizarre obsession that we have. So imagining that this is a fork with only 2 prongs, we have 2. But now we're going to keep on adding the regular forks to it. Okay, so how many prongs do we have here? It's 6, right? 6? Oh, I'm in jail there. Okay, but what if we add 3 more regular forks to it? Remember, this is the unique prong. It's special. So if we add 4 more other ones, how many will we have? So we have 6 with these 2. If we add 3 more, it will be an extra 12, right? So it'll be 18 prongs. So those are some patterns. You can identify it. Now, if you look in your textbook, you'll see all kinds of other examples. And they say one of the ways you can find a pattern is to use some cups and balls and then put an unknown number of balls in each cup. And kind of like, and that can change depending on like the number of prongs in a fork, the number of balls in a cup, in order to establish a pattern. That being said, it says here's one method you can do this, but usually when you're writing a test, you don't have an ample supply of cups and balls to do your calculations. So it's good to demonstrate, but not really your go-to method. So those are some patterns. I think you get the idea. Topic 1 talks about, can you describe a pattern? Can you say how every time we add a fork, we get 4 more prongs? That's really all there is to topic 1. It is sometimes fun to bend and break things though, right? Okay, other than hearts. Okay, so secondly, we're going to talk about expressions. So an expression is a representation of some kind of relationship. Now that expression can be just a number. The number 4 is an expression. If I asked you how many prongs are on a fork, you could just say 4. And 4 is an expression by itself. I'm going to actually write some stuff down here. Okay. So 4 is an expression. I'm using a binder so I don't get ink everywhere. Okay. But what if I asked you to write an expression that could tell us how many prongs we have for any given number of forks? Whether we have 0 forks, whether we have 1,000 forks, whether we have 6 billion forks. I want an expression that is truthful no matter what. Now, that will vary, right? It'll vary depending on how many forks we have. And that's why we have something called a variable. Here's the spelling of variable. Oh, yes. Isn't it beautiful? So a variable is a figure that can change. The value can change. So a number with a changing value. And usually, this is where we get to the hardcore algebra here, we express variables with some kind of letter. And the most common letter that you will see is the letter X. Sometimes you'll see Y, or you could see any letter. Over the course of your work, you'll see all kinds of different letters. Now, the very important thing with a variable is that you always explain what does the variable mean. Because you might solve and figure out what the number is, but if you don't know what that number actually means, what's the purpose, right? It's like eating porridge with a straw. It just probably will get stuck in the middle and be pointless. So we also see when we're looking at expressions, and so now to look at a variable, for example, if we said that there were four prongs to every fork, an expression that I could use is 4x. And we would say x equals the number of forks. So take a look right here. So this is our expression. This is our expression there, right above the pen, for the how many prongs we have. If we were asked what's an expression for the number of prongs, we could say 4x, because it's 4 times whatever the number of forks is. And you'll notice that a multiplication symbol isn't here. The multiplication symbol isn't here. We assume if our number and our variable are next to each other that it is multiplication. If it is division or addition or subtraction, there will be signs. Multiplication, there are no signs. So now our constant, when we're doing an expression, here, the number 4 is always number 4, right? It doesn't matter what planet you go to, 4 will be 4. So that is a constant. So a number with an unchanging value. And you might see in the textbook the definition. It might have a different focus. It might be worded differently. Just do keep in mind my definition is better. Okay, constant is a number with an unchanging value. Of course, I was missing a word. So now my definition is better. Okay. So there's one more part of expressions that we want to understand, and that is the numerical coefficient. And now that sounds fancy, but it's actually not something that you haven't seen before. And you can go around saying numerical coefficient, impress your friends, your family, the skunks that live under your stairs. So the numerical coefficient in this case, take a look here. When we say 4x, yeah, we think of 4 as a constant, we think of x as a variable, but when a constant number is multiplying that variable, it's known as the numerical coefficient. Because it's 4 times something, we don't know what that something is yet. So that is the constant number that is multiplying a variable. Okay. And the beautiful thing about the textbook is that these definitions are in the margins too, so you can get a nice reminder for you. Constant number, for yourself rather, sorry for the grammar. Constant number that is multiplying the variable. Okay, here we go. So I want to go back actually to our example with the broken fork. We're going to identify what expression this would be. So we had our 2 prongs here. Remember, our expression is for the number of prongs. You know, if you wanted to, you could do an expression for the number of forks. Say that your variable is the number of prongs, and you could go number of prongs divided by 4 equals our number of forks. We'll maybe do that later. Save that for a holiday or something. But I want to look at how could you write an expression for when we had this bent fork right here. So in this case, we had 2 little prongs here, but all the other forks that we added had still just 4 prongs each, right? So how could we write that? So once again, best thing to do so you don't stumble over your own thoughts is define that variable. So the way we do that, we always say let x equal number of forks. So for the most part, every time we add new forks, we are going to increase by 4 prongs, right? 4x. But there's the one little funny case, and that is that broken fork we had. So we're going to say 4x plus 2, because beyond that first fork, we are always just multiplying by an extra 4, adding an extra 4 for every fork that we add. So that is how you would write an expression when you have something else that is added. Kind of like if we said that we're throwing together a party and that we're buying some nice refreshments for everyone because we don't want people to get thirsty and leave the party for, you know, a water party somewhere else. Their little kids have their slip and slide and people leave our fancy dance to go drink from the slip and slide. No, we need refreshments, right? So an expression for that. So the costs are, think of it this way. We need to rent a place to host the party. And beyond that, we need to get a certain number of refreshments for each guest that we have. So let's say it costs $100 to host that party, plus $5 for refreshments for each guest we have. So that will be 100 plus 5x, and we're going to say let x equal the number of guests. So take a look at this expression here. 100 plus 5x. Beautiful. Okay. And so that's an expression for the amount of money we're paying. Now, usually when we're writing expressions, we like to actually have the terms. Actually, each of these is known as a different term. So everything that's separated by an addition or subtraction is its own term. But let's identify right here, just to review what we've gone over. So our 100 is always 100, right? We know no matter what, we're paying $100 to rent this hall. So that's the constant. We looked at the variable. The variable is x. Okay, we're very able to do that. And then our 5 is our numerical coefficient, because that's the number that is multiplying the variable. So however many number of guests we have, we multiply that by 5. Now, just one of the things, just as far as nice proper notation here, the writing down of it, in math, we generally like to have the terms that have the variables in them first. So a better way to write this, it'll give you the same value, is instead of 100 plus 5x, 5x plus 100. It's just a nicer way, a tidier way to write that. And that'll eventually come to grade 9 when you get to terms where it says x squared or x cubed. You would put them in the same order so that x squared would come before x, which would come before your constant. And especially when you're rearranging things, there's a reason you want to do that. So it's good to get into the habit early. So that is how we would write an expression. That pretty much takes us to the end of topic 2. Now there are lots of examples. You can build your familiarity, but I did just want to go into detail with that one example there of the parties, and I guess the forks too, to show you how you would write an expression. So the question is though, now that we have our lovely expression, how do we actually figure out, okay, how do we use it to figure out how much the party costs or how many total prongs we have? So that comes to topic 3, which looks at finding the value of an expression. And this one might be the most straightforward of them all as far as the topics go. All you have to do is replace that variable. Replace the variable with whatever number you want to find. So let's say that we have, how many guests do we have? Imagine if you invite all your friends in the world to this party. Okay, or yeah, okay, 3. Okay, we've got 3. So I'm going to take 5x plus 100. Let's use that one. And I'm going to replace that x with 3. So this is what it will look like. Okay. So you note the brackets. So whenever we substitute something for the variable, we put it in brackets there. And later on, you can probably drop those brackets if you haven't multiplied that number like we're going to. But that just shows, here's the step we've done. You want to work down. You want to show each step. You don't want to skip anything. Even if this is something you can do in your head, right? Some of you are thinking it's 115, right? Why do I even have to write this? No, you always want to show your steps, not just because we want to punish you and take away marks for not doing that, but because if you have any errors, then we can verify. We can see where did you go wrong. So even if it's simple, show your work. So 5 times 3 plus 100. So now that we've got rid of all the variables, all you have to do is follow your order of operations, BADMAS, and simplify, so to get it to one number. So we go multiplication first. 5 times 3 is 15, plus 100, and that becomes 115. And then if it's a word problem, you would say, if we have 3 guests, the party will cost $115. Will cost. And now, of course, if they all put their, some items or something in a safe spot, their coats, if you manage to sell their coats for a profit, you've made a tidy sum from your party. So yes, you want to write a sentence so that you know ultimately if you just have a number but you don't say what the number means, what's the point? Because remember, we are talking about different factors here. We're talking about the constant of what the hall costs. We're talking about the cost of the tickets. or the cost, sorry, cost of refreshments per person, and the total cost, right? So what number is it that you are finding? You might be given the total cost and asked figure out how much it costs for refreshments for each person. We could have expressions. Let's look at an expression where that's the case. Let's look at the forks again. So we talked a lot about how many total prongs we have, but let's say we know how many prongs we have and we're trying to figure out how many forks we have. Okay, so let's take a look at that. So we're going to say let's use a different letter though this time, shall we? Let's use a letter no one would expect. Let's use W. Okay, let W equal the number of prongs. Okay, so we know we're going to forget about that broken one for now, but we're going to say W divided by 4. This is an expression for our number of forks. Yes. Okay. So you might be wondering though, what about if we have that fork with the 2 broken prongs? How does that affect things? Well, let's take a look, shall we? Now for this, we'll take a look actually at an equation. An equation is something actually we'll look at a little bit more later on. It comes up more in grade 8. But with our equation, that's where we have an equal sign. So in this case, the only way an equation would be different in this case, we would say let W is the number of prongs. We could say X equals the number of forks. So, so equals X. So in this case, take a look here. Sorry, I messed up with my X. So W over 4 equals X. So you see, it basically tells us, in this case, what does the expression mean. That's the only difference between an expression and an equation. That there's an equal sign, there are 2 sides to an equation. So in this case, we have W divided by 4 equals X, was with just the regular forks. And so, but we saw though, that if we take our total number, we have W minus 2 over 4. So this shows us this gets rid of the number of prongs from that 1 fork, right? We want to take that out of the way, but we know that that is a fork. Even though it's broken, it still counts as a fork. So we want to still count that. So that is going to be plus 1 equals X. So in this case, yeah, I showed you what an equation was. We didn't need to say the equals X, but I wanted to do that. It just kind of helped me get things together in my head to have an expression, to have an equation there. But if we're just looking at the expression, let's see if that actually is true. Let's see if our expression actually works. Let's substitute a value. Okay, so let's not go too high here. Let's go with 10. Let's go with 10, shall we? Let's say we have 10 prongs. Okay, so we're going to substitute 10 into the W. Gosh, I hope this works or I'll be embarrassed. I'll be humiliated. I'll be forced to resign on the internet for all the millions of people to see. Okay. So, take a look down here. We've substituted 10 prongs. We know we have 10 prongs, but what we don't know is how many forks we have. So 10 minus 2 over 4 plus 1. Note that, take a look here with this division. When we're dividing, we're not just dividing the W here. We're dividing the W minus 2. So you can't actually do any division until you've simplified the 10 minus 2. Okay, so 10 minus 2 was 8. It still is 8, actually, to this day. So now we have 8 over 4 plus 1 equals X. So 8 divided by 4, you know that to be 2. Oh, I'm running out of space here. Oh, no. Okay, you know what? I'll make a new column on the left. Okay, so 2 plus 1 equals X. You know 2 plus 1 equals 3. So take a look here. If you have 10 prongs, you have 3 forks, including that broken one, in that case where you have that broken one sitting around. Let's see if that's really true. If we have 3 forks, do we have 10 prongs? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It works. Expressions and equations, they're real things. Okay, fantastic. So that is how you substitute a value into an expression or an equation. Lastly, we're going to look at graphing these. These are called linear relations, actually, all of these expressions with which we've been working. And that means, I know it sounds fancy, but a linear relation, get a new piece of paper here. A linear relation just means that it is a relationship between a couple of different variables, in this case the forks and the prongs, that when graphed will form a straight line. The first 4 letters of linear are line. Okay, so this is how it's spelled, linear relation. So a relationship between 2 variables, and I'm doing B/W for between, that will form a straight line when graphed. Okay, so one of the key things we're going to want to do, it's usually tough to go just straight from your expression to a graph. So we're going to make a table of values. So we're going to write with our forks how many forks we have, and for each number of forks that we have, how many prongs are present when we have that many forks. It forms a straight line when graphed. Okay. These fumes from this marker, oh, they're starting to fill the room. Okay. Don't light a match when graphed. Yes. Okay, so let's take a look here at our expression, and let's include our little broken pronged fork that we had. So we have a table with 2 sets to it, 2 columns. So we have our number of forks and our number of prongs. Okay, and I'm going to put F for forks and P for prongs. Okay, so then you're going to have a nice table, like a T-chart here. So if we have 1 fork, so actually it should say the number of intact forks. Because keep in mind this, if every variable, even though it can vary, is going to be the same to itself. So every F should be the same. In this case, this is not the same. This is something different from the other forks. So if we have 0 intact forks, we still have this. We can't get rid of this. So if we have 0 intact forks, we do still have 2 prongs. If our expression is that, if our expression for prongs is 4F plus 2. So 4F plus 2. This is the expression that we're going to be graphing, okay? So 4F plus 2. So if we have 0 intact forks, we do have 2 prongs from this one. Yeah, okay. This is like the bad one, the bad fork. Yeah, that's right. Never completed its homework on time, and this is what happened to it. Okay. But now we're adding a new fork. Yes. So now we're up to 6. Take a look at our beautiful table of values. It's growing. Okay. And when we add 2, we get up to 10. When we get 3, we are then up to 14. Okay. Yes. Now you'll note that. Now I mentioned how, okay, the broken fork has to count as a different one. You might be thinking, wait a second, when we did that equation actually to figure out the number of forks, why was it that we did actually include the broken fork in that? I know what you're thinking. I'm going to get some complaints about this, some angry comments. Okay, no, actually the reason was we actually accounted for that in our equation. or if you get rid of the x, could be an expression. Because see this plus 1 here, the plus 1 represents that broken fork. Okay, so we had our lovely division here for the intact ones. Or sorry, for the number of prongs for the intact one, but then we knew there was an extra fork, so we accounted for that with a plus 1. In this case, though, when we're looking for the number of prongs, when that is our focus, we can't consider that that broken fork as one of the ones we're multiplying, right? Just like we weren't dividing the broken one when we were going the other way. Sorry, that was just on my mind. That was why there was the protracted silence there. Okay, and now I only have so many forks here because I'm not exactly made of money. I spent it all on yogurt jars that I broke in an earlier demonstration. Okay, so of course you could go on forever, right? You could buy all the world's forks. It goes for a while. Our graph is only going to be limited size, of course, because of the finite nature of the universe. So now we have the information we need to actually plot this on a graph. So we're having our one axis. If we're focusing on a responding variable, the responding variable is the prongs here. And what we're manipulating is the number of forks, because you can choose how many forks you buy when you go to the store. You can't say, hey, I'd like to get 17 fork prongs today. And so we're going to put this on a graph. And this is really comes back to our coordinates and design unit. So knowing the x-axis and the y-axis. We're going to want to put our manipulated variable on the x-axis, and we're going to want to put our responding variable on the y-axis. Okay. Here we go. And you'll see, it should, if it is truly a linear relation, it should come out to be a straight line. Oh wait, I have a ruler somewhere. Where'd it go? Oh yes, here it is. Oh my goodness. You'll be impressed. Yeah, okay. There we go. Nice, fancy. Corporate advertising. How about that? Okay, that's how I'll become a fabulously wealthy YouTube star. Okay, so making my graph here. Got my x-axis and my y-axis. The important thing is to label it. And in our coordinates and design unit, what we'd often do is we would say x and y. But of course, well, we don't need just an x and y sitting there. We want to know what these axes actually mean. So along our x-axis, we have our number of forks. And on our y-axis, we have our number of prongs. Okay, so 0. And I'm going to, because these are all even numbers and to save space, I'm going to do some little dashes in increments of 2. That seems like an appropriate thing to do. Okay, I'm up to 18 now. That should be good. Okay, and now our number of forks. Now because our, well, golly, because our number of forks we're going up by 1, let's go up by 1 each time, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That'll be more than enough, and I'm just going to label it every 5 spaces, right? You only have so much room to write numbers, and let's not get a little overcrowded here in our writing. Okay, so now all we have to do is, using our table of values, we are going to be plotting these on our graph. So we have our x value, and the x-axis is this one, and our y right here for the prongs. Okay, so when we have 0 intact forks, and forgot to write intact on the graph, when we have 0 intact forks, we have 2 prongs. So take a look right here. We have our lovely little point right here on the 0. It's right here on the axis. When we have 1 fork, we then have 6 prongs. When we have 2 forks, we're at 10 prongs, right? And let's go as high as we can on the y-axis. 3 forks will then be 14 prongs. I'm looking off the table of values here. 4 forks will be 20 prongs, and that is actually beyond where we had on our graph.
This is a national emergency. Important instructions will follow.
Now, it's at this point, folks, that I must apologize. There were a couple mistakes that I've made along the way. One of them you may have noted that, yes, I had the wrong value on there because although I said I would rely on the table of values, I was a prideful, egocentric fool. Take a look at the table of values. Take a look at my graph. Yes, I had plotted that 4 forks would be 20 tines when, as you know all too well, 4 forks gave us 18 prongs. 4 intact forks, that is. So I fixed the graph. But as you saw from the emergency alert, it's not the only thing that was missing from my graph. It was also a title. And now for all you know, I would have added a title to the end of this anyway. But truth be told, no, I hadn't added a title. So we always want to make sure we add a title. What should we call this? The freak fork collector? Yes. The freak fork collector. Collector is collection of freak forks. You don't have to get super creative with titles. It's not something you get marked on, but you do want to have a title that tells you what the graph is about. So, here we go. So, as we saw, that's why I wanted to use the binder because now I got ink on my computer. Okay, there we go. Now it's on my skin instead. Okay, so as we saw, now using this graph, we could then extrapolate or figure out with any number, if your graph was large enough, how many tines or prongs we had with that number of forks. Now it's also a good habit to write your variable right on your graph too. So you can write prongs and forks P and F right there. Okay. So that's our look at all things patterns and expressions. So how to identify a pattern and just describe it with words, how to write an expression actually as a set with numbers. We look at variables, constants, numerical coefficients, how to substitute the values into an expression, and how to graph a linear relation, and to establish the relationship between two variables, in this case, prongs and forks. So if you have any questions, please, I'm always an email away. I definitely hope you watch this in several shorter sittings rather than the whole thing in one go, unless of course this is your family movie night. And to use an old expression, see you later.